spend a lot of time thinking about Mars, mostly about if it could someday support human life. Scientists are constantly researching and experimenting with different ways people could potentially live on the red planet, whether that's underground or in specialized habitats. And we've talked about that research a lot on SciShow Space, enough to make a whole compilation of videos about it. One thing we know isn't a good idea is to just hop out of our spacecraft and walk around like we do here on Earth. And the reason why is a lot more interesting and complicated than I would have first assumed. Here's Hank breaking down exactly how long you could survive on Mars without a spacesuit.
Mars is a well-known subject here on SciShow Space, whether we're talking about the challenges of future human exploration there, or following the amazing things Curiosity is doing right now. But here's one question we have yet to answer. How long could you just survive on the surface of Mars without a spacesuit? The good news is that you'd last longer than you would on Venus, which is probably the most inhospitable place on the surface of any planet. The bad news is that you're still gonna pass out in less than 30 seconds and be dead in a minute. Maybe 90 seconds, if you're lucky. Now yes, Mars and Earth do have some very basic things in common. Like Earth, Mercury, and Venus, it's a rocky planet, so it actually has a surface that you can stand on, which is nice. But because it's just over half as big as Earth and much less dense, Mars has only 38% of Earth's gravity, so as you're fumbling for your keys to get back in your spaceship or whatever, your movements might be kind of jerky and sudden and weird. But that is definitely the least of your problems right now. It's also very cold, for one thing, thanks both to its thin atmosphere and its greater distance from the sun. With not much atmosphere covering the planet's surface to retain heat, the average temperature on Mars hovers around minus 60 degrees Celsius, though the extremes range from minus 125 at the poles to a balmy 20 degrees at the equator. 20 degrees, that's perfectly livable. That's like Earth-like. Well, then there's the radiation problem. The atmosphere is way too thin to absorb ultraviolet light from the sun the way the Earth's does. It also doesn't have a magnetic field the way that the Earth does, so all that radiation is just hitting the ground pretty much at full strength. And it won't kill you right away, but should you survive your jaunt on the Martian surface, problems will come up later as that radiation starts to cause mutations in your cells. But your biggest problem is the atmosphere itself. The surface of Mars is not technically a vacuum, but it is about as close as you can get without actually being in outer space. What atmosphere there is on Mars is composed almost entirely of carbon dioxide with trace amounts of nitrogen, argon, and oxygen. That's enough of an atmosphere to support some clouds and wind, but the surface pressure on Mars is about 1/100th that of what we have on Earth. And the human body does not do well when suddenly exposed to extremely low atmospheric pressure. Contrary to what you might have heard, exposure to vacuum-like conditions will not cause your blood to boil or your eyes to pop out of their sockets. But with so little air pressure, many of your bodily fluids will start to vaporize. That means your sweat, mucus, saliva, and tears are going to evaporate within a few seconds, which is going to be uncomfortable. Also, all that water in your body is about to turn into water vapor. Thanks to your strong and elastic skin, you're not going to explode, but you will become bloated before you've had a chance to take in the view. The release of all the gases in your blood and other fluids will basically give you a very quick and very severe form of the bends, the decompression sickness that affects divers who return to the surface too fast. So if you do become part of that generation of explorers that makes it to Mars, and I really hope that you do, for the love of Pete, don't forget to wear your spacesuit.
Okay, so wear a spacesuit on the surface of Mars. Got it. But even if you take all the health and safety precautions, living on Mars would still be pretty inconvenient compared to what we're used to now. In this video, Reed unpacks the hardest aspects of living on Mars.
Lately, there's been a lot of talk about building a colony on Mars. There's still a lot to do before we get to that point. Like, we should probably figure out how to get people there, but even if we did set up a human habitat, we'd still have some huge challenges to overcome. Because traveling to and living on the red planet would be more dangerous than basically anything we've ever tried. Here are 3 of the biggest challenges the Mars colonists would, or will, have to face. The danger starts long before reaching the Martian surface. Depending on exactly when and how our astronauts launch, it will take the crew somewhere around 7 months to get to Mars. And as soon as they leave the protection of Earth's magnetic field, they'll be exposed to the intense radiation environment of space. This radiation is mostly made of tiny subatomic particles like protons and neutrons. Many stream out of the sun as part of the solar wind, while others, called cosmic rays, come from all over the galaxy. And sometimes these particles can strike a bit of DNA as they pass through the human body. Each hit can randomly change a little of someone's genetic code, and that can lead to mutations in new cells that ultimately cause cause problems like cancer or heart disease. Thankfully, because we're protected by the Earth's magnetic field and atmosphere, we aren't exposed to most of these particles, but things aren't the same in space. Although astronauts take precautions, spending 6 months on the International Space Station results in absorbing about 3 times as much radiation as the US annual legal limit, and a trip to Mars would be over twice as much as on the ISS. And if there happened to be an explosive solar flare during the trip, the crew could receive a lethal dose of radiation in just a few hours. Since Mars lacks a global magnetic field and doesn't have much of an atmosphere, things don't get a lot better once the astronauts land either. Over about 500 Earth days, they would receive about as much radiation as on the trip there, and that would really add up over a lifetime. To protect our first interplanetary settlers, scientists have a couple of ideas that would make MacGyver proud. First, it turns out that water is very effective at absorbing radiation because it's rich in hydrogen, which is just the right size to block these subatomic particles. And water is something the astronauts will already be bringing with them. So, one option is to line their spaceships and habitats with tanks of it. Another option is tunneling underground to escape the radiation, or setting up shop in giant empty lava tubes left over from when Mars was volcanically active. Of course, astronauts don't need to worry about radiation if they starve to death first, and growing food on Mars won't be a picnic. Well, actually, growing food might not be too terrible. Laboratory experiments suggest that it is possible to grow plants in the powdery Martian soil, and Mars's atmosphere is full of yummy carbon dioxide for photosynthesis. What might be more tricky is not dying from the food you grow. See, Mars's surface is full of perchlorates, a class of salts considered industrial waste here on Earth. Perchlorates overwhelm the body's thyroid gland by blocking its ability to absorb iodine, which is normally used to produce a hormone that regulates your metabolism. In the US, it's regulated in things like groundwater at the state level. Massachusetts, for example, sets the legal limit at 2 parts per billion by mass. Meanwhile, on Mars, perchlorates are found at a rate of around 6 million parts per billion, which is just a tad higher. Just like we can clean up soil here at home, it's possible to do the same thing on Mars, like by introducing microbes that eat perchlorate as an energy source, which of course would run the risk of contaminating Mars with even more Earth life, and that's a whole different problem. So either way, I'm gonna let you take the first bite. To power all that soil cleanup, plus basically everything else, settlers will need a reliable source of electricity. The obvious answer is to just throw up a bunch of solar panels and call it a day. But that could be a big mistake. See, every year, Mars suffers from dust storms the size of Earth's continents, and on average, those cover the globe about twice a decade. The thin Martian atmosphere means these windstorms wouldn't blow over the solar panels, but all that dust flying around blocks an enormous amount of sunlight. When the Mars rovers Spirit and Opportunity got trapped in the last global dust storm in 2007, they were reduced to operating just a few minutes each day. That's okay if you're a robot, but not so good if you need to do things like, breathe or see at night. To get around this, the first Martian colonists will need to bring a different kind of power source, like something based on plutonium. Because plutonium doesn't care if the sun is out. So it's not that there aren't solutions to these problems. We could clean up the soil, build radiation-proof habitats, and figure out a reliable power supply. The thing is, there are a lot of problems, and finding the answer to each of them in a way that doesn't break the bank will be a real challenge. But hey, people on Mars, if we can get that far, we'll figure out the rest.
So humans living on Mars would be really cool. But we can't forget that where you have life, you also have death. Hank and Reed have already talked a little about all the things you would need to keep people alive on Mars, but what happens to your body if you die there? Someday, somebody's going to die on Mars. Death is not fun to think about, so let's just assume it'll be after one of the founders of the first Mars colony has lived to a ripe old age and watched their people grow and flourish, and it'll all be very peaceful. But no matter how or why it happens, the science of what comes next is super interesting. First, any burial plans are going to have to consider international law because there are United Nations charters against contaminating other planets. And unfortunately, we humans are covered in and filled with contaminating microbes. And if a person is going to die on the red planet, all those microbes are going to have to be killed or contained. And there are a couple options for how to do it. The first is cremation, or burning a body into ashes. Fire will kill all those microbes, and it's a practice that many communities already use and have rituals around. But there's also an alternative that's being developed specifically for use in space. It's called body bag, and it's pretty sci-fi. In 2005, NASA contacted the Swedish company Promessa, which specializes in environmentally sound burials and cremations. NASA asked them to look into a system for handling remains that can be used in space. So they came up with the body bag, which is basically just an adaptation of Promessa's existing process, although it hasn't been done to anyone on Earth yet. First, the body of a Mars traveler would be stuck in a weatherproof bag. It'd be cooled down and then exposed to liquid nitrogen for a bit. This would deep freeze the body and make it really brittle. Then the bag would be shaken up by a machine until the body became a powder, which is really effective for saving space, and that's always important on a mission, even if it's kind of creepy. Still, liquid nitrogen doesn't always kill bacteria. It can also preserve them, causing them to stop growing without actually dying, so the body would have to stay in the bag forever. But it's at least an option. Now, if cremation or bag of powder options aren't available, like if someone's spacesuit breaks and they're exposed to the Martian elements, the process would go a little differently. For one, they'd technically be violating international law, but there would be more immediate problems at that point. To know how a body would respond to being left alone on Mars, scientists can actually study a similar environment on Earth, the Atacama Desert in Chile. The Atacama is one of the driest places in the world, and it's super high up, with peaks reaching elevations of about 6,000 meters. And the higher up you are, the thinner, cooler, and drier the air. It's a little like Mars. Hundreds of years ago, the Atacama was part of the Incan Empire, and the Inca had a practice called capacocha. These were ritual child sacrifices, which, to be clear, are horrible. But the bodies of these children have helped scientists with research hundreds of years later. Because, despite all that time, the bodies haven't really decayed. In the Atacama, it's too cold and dry for bacteria to grow well, so the bodies became natural mummies. And that's close to what would happen on Mars, too. It's generally colder and drier than it is here on Earth, so not much would happen. The bacteria on or in someone's body just wouldn't grow, or would grow much more slowly, so it would take centuries for a body to break down, if it decayed at all. Now, if someone died closer to the Martian equator, where the temperatures can get up to 20 degrees Celsius, the bacteria inside their body might start to decompose it for a while. But the process wouldn't go on forever. That's because Mars also has super high levels of bacteria-killing radiation that would finish the job. You're probably familiar with UVA and UVB radiation from sunscreen and sunglass labels, but Mars also has an extra kind, UVC, which has a shorter wavelength. Our atmosphere is capable of filtering out all UVC radiation, so life on Earth isn't great at dealing with it. UVC is also especially deadly because those shorter wavelengths carry a lot more energy, so it would probably kill most of the surviving microbes. So if someone died on Mars and there was no way to recover the body or turn it into a powder, it would probably become a mummy over thousands of years. Admittedly, there is a chance some of those bacteria could survive the UVC radiation thanks to certain mechanisms that can repair radiation damage. If they did, they would probably decompose the body over time. But then Mars would be home to a bunch of radiation-resistant bacteria, which is a whole new problem, or horror movie, and that's probably why the United Nations would require bodies to be sterilized or contained. Thinking about people dying on Mars isn't exactly something NASA or any other space agency really wants to do. But it's an important part of planning for the future. And even if it is a little morbid, the science behind it is definitely worth thinking about. I love science so much. Okay, before we turn into Mars mummies, though, there are other big picture ideas for how to potentially turn Mars into Earth 2.0. Here's Reed to talk about terraforming our closest neighbor.
In some ways, Mars kind of sounds like a cool place to live, doesn't it? The red soil, the craters, the dormant volcanoes, seems pretty scenic. And if you chose the right real estate, you could use one of the Viking landers as like a lawn ornament or something. But of course, you'd have to be okay with temperatures around -60, an unbreathable atmosphere, and deadly doses of radiation, which for most people are kind of deal breakers. But technology can do some fantastic stuff. And scientists who study terraforming, the science of transforming a planet to support human life, have put a lot of thought into changing these things. Turns out, with a few centuries worth of effort, we might be able to make Mars habitable for humans. But I'm not gonna lie to you, it would be really, really hard. A whole bunch of major things would have to change. Most importantly, Mars needs an Earth-like atmosphere. There are a few theories about how to create one, and they have a lot to do with the planet's history. In its younger days, about 4 billion years ago, Mars was actually pretty similar to Earth. It was warm and wet and had something of an atmosphere. That's because the Martian soil absorbed a lot of carbon dioxide and nitrogen that was floating around in the air. But then, active volcanoes recycled those materials by baking them out of the soil, so they could be absorbed again. The result of this was an atmosphere that mostly stayed put. Asteroids that kept hitting the planet helped out too, keeping it nice and warm. And back then, Mars had a magnetosphere, a planetary magnetic field that protected the atmosphere from being stripped away by solar winds. But then the planet cooled and lost its magnetosphere. There were fewer asteroid collisions and its volcanoes stopped erupting. Without all that help, Mars's surface absorbed a lot of the compounds from its atmosphere and lost most of what was left to solar winds, leaving a freezing, dry, barren world. Sounds pretty bleak, I know. But given what we know about Mars's history, with a little tweaking, we might be able to bring that atmosphere back. Basically, we need to start a massive global warming effect, something that humans seem pretty good at. And scientists have come up with 3 main ways to do it. The first and easiest way might be to just build factories that would basically turn carbon, fluorine, and sulfur in the Martian soil into greenhouse gases and pump them into the atmosphere. This would unlock one of Mars's greatest assets when it comes to warming things up, the thick layer of dry ice or frozen carbon dioxide that covers its south pole. An initial burst of greenhouse gases could cause this ice to sublime directly into vapor, releasing carbon dioxide gas that would help trap more heat from the sun, in turn releasing more greenhouse gases. But all that would take a while, and it would be tough to supply those factories with the resources they'd need. So another method might be to build giant 200-kilometer wide mirrors in space. They'd reflect sunlight onto the Martian ice caps, raising the surface temperature and releasing that carbon dioxide. If neither of those ideas worked, there's always the possibility of bombarding the planet with asteroids. In this scenario, we'd capture asteroids on the edge of the solar system and use rocket engines to propel them into Mars. The ammonia in the asteroids would act as a greenhouse gas. But each asteroid would be like a 70,000 megaton hydrogen bomb. So, aside from the obvious logistic problems, we'd have to do this way before humans were ready to set up shop there. And even then, once the atmosphere had some greenhouse gases in place, it would still need an ozone layer, a shroud of molecular oxygen that would absorb some of the sun's dangerous ultraviolet radiation. So there would have to be yet another step, where we introduce organisms like cyanobacteria or lichens, which would help enrich the soil and release oxygen that could eventually form ozone. Once the ozone layer was in place, the final ingredient for an Earth-like atmosphere could be added: nitrogen. This could be introduced by asteroid bombardments, or bacteria could extract it from the nitrogen-bearing compounds locked in the regolith, the rock layer just above the Martian bedrock. Easy peasy, mission accomplished, right? No, not quite. Mars would also need a way to hold onto its atmosphere and keep it from being stripped away by solar winds. Basically, it needs to get its magnetosphere back, which is the biggest problem with terraforming, because we really don't know how to do that yet. Earth has a magnetosphere, which we're pretty sure is formed by liquid metals in the core that create an electromagnetic field as they slosh around when the planet rotates. The same effect would happen on Mars if we could only figure out how to melt its core, which appears to be solid metal, not liquid. So if anyone has any suggestions on how to liquefy the middle of Mars, we're all ears.
As Reed mentioned, a magnetic field is a pretty big deal for humans and our DNA. So could we give Mars a magnetic field? There's been a lot of talk lately about sending humans to live on Mars, but it's easy to say that and a lot harder to actually do it. A big part of that is because Mars isn't especially friendly to human life, or life at all. It's freezing with a super thin atmosphere that not only makes it impossible to breathe, but also doesn't give you much protection from all the deadly radiation coming from space. To change that, we'd have to terraform Mars, changing its geology and climate to be more like Earth, which is usually a subject more appropriate for sci-fi than science. But at the Planetary Science Vision 2050 workshop in early 2017, a group of scientists led by the head of NASA's Planetary Science Division suggested a way we might get started. Their plan? Build a giant force field, a protective magnetic field for the planet. And as weird and impossible as that sounds, it's not totally science fiction. The idea is that this magnetic field would replace the one Mars lost long ago, which would then let the planet build up a thicker atmosphere. Billions of years ago, Mars might have looked a lot like modern-day Earth, with a magnetic field, a warm atmosphere, and oceans on the surface, with about as much water as our Arctic Ocean. But for reasons scientists still don't fully understand, Mars lost its magnetic field about 4.2 billion years ago, and everything kind of went downhill after that. Without a magnetic field to block the charged particles streaming from the sun, aka the solar wind, Much of the Martian atmosphere got stripped away over the course of about 500 million years. Without a thick atmosphere to trap heat, the planet froze and its oceans were lost forever. Unless we can find a way to bring them back, that is. Even today, 4 billion years later, and with barely any left, Mars can lose up to 1 kilogram of atmosphere to space every second. We'll never get back all the stuff that's escaped into space already, but there's still gas leaking out of the planet's crust, so there's at least some hope of building it back up. If we could, that would provide more protection against the radiation, plus help warm the planet a bit. Astronomers also think there might be enough water trapped in the polar ice caps to rebuild about 1/7 of the ancient oceans, if we can get the climate warm enough for the ice to melt. But first, we have to get the atmosphere back, and that's where the NASA team's big idea comes in. If we could block the solar wind from stripping away the atmosphere, it might start to build back up again. At first, that might sound like it involves building something the size of a planet, and that's not super practical, but the researchers proposed a way to get around that problem by taking advantage of the fact that the solar wind is only coming from one direction, the sun. So all we would need to do is block the sun. Kind of like what the moon does during an eclipse, which would still require a huge shield, but we wouldn't have to build a giant solid thing. It would just be a magnetic field. And that might actually be practical someday. All we would have to do is figure out how to generate the field. Then it would reach out into space and do the rest. More specifically, the team suggested putting a field-generating device about 1 million kilometers from Mars. The magnetic field would have to be a bit stronger than the Earth's, which would be hard on such a large scale. But it's something we could probably figure out how to do. To understand what that would do to Mars, the researchers followed a 2-step process. First, they used computer simulations to calculate what a magnetic shield would do to the atmosphere. Then they used climate models to predict what effects those changes would have. The results suggested that Mars's climate would change a bit, but that we shouldn't get our hopes up too much. Although a strong enough field would stop the solar wind, that's only one of the processes making Mars lose its atmosphere. The planet's weak gravity and molecular interactions with sunlight also contribute. In a process called photoionization, atoms and molecules in the upper atmosphere can absorb energy from light and break apart. Some of those pieces end up with enough energy to break free of Mars's gravity and escape to space, which is not good if you're trying to keep the atmosphere around. And although the global temperature would rise, this would mostly happen near the equator, which is not where the ice is. In fact, because of the way atmospheric physics works, it might even get colder at the poles than it is now. That would keep all the dry ice, which is made up of solid carbon dioxide, trapped in the polar ice caps instead of vaporizing it into gas that would thicken the atmosphere. Plus, that dry ice is sitting on top of the water ice needed to refresh the global oceans. And even if the shield was enough to thicken the atmosphere and bring back the oceans, it would take a while. Like, the researchers didn't even have an estimate of how long. So I wouldn't count on taking a boat down Valles Marineris anytime soon, but the idea is intriguing because unlike many other terraforming ideas, the technology seems pretty doable. MRI machines use fields even stronger than what this research calls for. We just need to figure out how to make a field of the right shape and size and get it into space. And the idea of putting something between the sun and Mars isn't that different from some proposals for dealing with climate change here on Earth. For example, some scientists have suggested that one day we might be able to launch what would basically be a giant pair of sunglasses to block some of the sun's rays and cool the planet. But before we give Mars its very own Hylian shield, there's another question that needs to be answered. Even if we can do this, should we? There's a lot we still don't know about our planetary neighbor, and we still haven't completely ruled out the possibility of alien life over there. If there is life on Mars and we totally transformed the planet like this, we'd basically be destroying its habitat. But with no immediate plans to actually give Mars a magnetic shield, hopefully we have plenty of time to work those questions out. All this talk about Mars is making me kind of miss Earth. Luckily, we can learn a lot about Mars right here at home. Here's Reed again to talk about what studying Earth can tell us about life on Mars.
Mars is a pretty astounding planet, and our missions to Mars have been making fascinating and groundbreaking discoveries for decades now. But some of the coolest Mars research isn't actually conducted on Mars. It's done here on Earth, in environments that are a lot like Mars, either as it is now or as it was billions of years ago. They're called terrestrial analogues. And the research done in these environments has changed the way we think about life on Earth, Mars, and rocky planets in general. There are a couple main reasons to study terrestrial analogues for Mars. One is that it's a practical approach to space research. It's difficult and expensive to get to Mars, and we're already here on Earth for free. And we have way too many questions about Mars to be able to answer all of them with just the tools we have over there. So doing Mars-related research on Earth lets us learn more about both Mars and Earth than we would if we only did our Mars research on Mars. Another reason is that the best way to solve some Martian mysteries is to compare Mars to Earth. One of the biggest questions when it comes to Mars is whether it ever harbored life. And looking for life in places on Earth that resemble Mars can give us a better idea of what kinds of adaptations life might have developed to survive on Mars, if it ever did evolve there. Knowing more about where life can theoretically survive could also help us figure out where to look for signs of life on Mars. So some of the best analogues for Mars here on Earth are useful not just because of the insight they give us into Mars as a planet, but because of the insight they give us into Mars as a potentially habitable planet. Like the Nika mines in Mexico, for instance. The Nika mines and caves are probably similar to underground environments on Mars, which we know exist but haven't been able to explore because it's super dangerous to send a rover underground on another planet. The caves at Nika are probably especially similar to what it would have looked like underground on early Mars, when the planet was much wetter and warmer. Like most mines, the Nika mines are deep underground, but unlike most mines, they're ridiculously hot and humid. Like lethally hot and humid. Researchers have to take tons of precautions, including wearing special ice suits with oxygen supplies to make sure they don't die. The mines also happen to be incredibly beautiful, home to huge caverns containing massive gypsum crystals that dwarf elephants, let alone people. And from experiments started around 2009, researchers discovered something incredible. There were dormant microbes in fluid inclusions in the crystals. Basically, tiny little pockets of water that form in a crystal as it grows. And the researchers were able to revive them. That tells us two things. First, that if life ever evolved on Mars, it might have been able to survive in similar cave environments. And second, that those are really good places to check for signs of life, past or present. This strategy of surviving in rock is really weird, but super useful. And a similar strategy has been taken up by the microbes living in another place on Earth that's a great analog for Mars: the McMurdo Dry Valleys in Antarctica. The dry valleys are basically the opposite of the Nika mines. They're super cold deserts, and they're a lot like the dry, freezing lowlands of the Martian North Pole. Researchers working on projects for places like NASA use the dry valleys as a place to test equipment destined for Mars. And astrobiologists use them to explore Mars's potential for habitability. Because even though the dry valleys are really cold and dry, scientists have discovered a few forms of life that manage to live there, and some of them have adopted a similar strategy to the life in Nika, despite the huge difference between their habitats. There are endolithic phototrophs in some of the rocks at the dry valleys. Endolithic means inside rock, and phototrophs use photosynthesis, and that's what these organisms do. They live inside rock, but they still use photosynthesis. The rocks containing the endoliths are mostly sandstone, which can transmit some light through it. So the microbes inside the rock are still able to photosynthesize even though they're not directly exposed to sunlight. And they get a nice little rocky home to protect them from the harsh Antarctic desert. Both Nika and the dry valleys host life that has taken an approach to survival that could be outstanding on Mars. Since Mars doesn't have much of an atmosphere and has no magnetic field, its surface is constantly bombarded by UV light. If potential life on Mars lived inside rock or underground, that might be enough shielding from radiation for them to have survived for a good while during Mars's early history. And the neat thing about these strategies, especially the endolithic strategy, is that it can work anywhere you have the right kind of rock. This could work just as well at Mars's North Pole as it could in its southern highlands, as long as the rock is transparent enough. So these discoveries have given us a window into Mars, and we didn't even have to leave Earth. As we continue to explore beyond our solar system and find rocky exoplanets, this research becomes even more important. It helps us define what it means to be habitable for all planets, not just our own. And a bunch of little underground microbes just gave me an existential crisis.
Earth is so awesome, and so is Mars. Thanks for learning about our neighbor planet with me. If you want to keep up to date on all the latest Mars news, be sure to go to youtube.com/SciShowSpace and subscribe. And if you listen to Hank and his brother John's podcast, Dear Hank and John, you'll get a little snippet from Hank every week about the news from Mars. You can listen to that wherever you prefer to get your podcasts.